In this problem, we shall study collisions in one dimension and center of mass and relative motion, relative momentum. So let me write collisions in one dimension and center of mass and relative motion. All right. So, for example, in one dimension, we have two objects, m1, m2, and they have velocities v1, v2. If v1 is larger than v2, it will eventually catch up and it will make, there will be a collision. And the problem is, given in general, given v1 and v2, find v1 final. So given v1 initial, v2 initial, find v1f, v2f, depending on the type of collision. Depending on the type of collision. So we will explain all this. When two things collide, and then they will separate again, if we call this system, let me call this system S. If there is no external force on this system S, then the total momentum, so if F external on S is equal to 0, then the momentum of the system is conserved. That means P1 plus P2, which we shall call P center of mass, this is conserved. Let me just add something here. Suppose M1 and M2 collide. So here is M1 and here is M2. When they collide, they apply collision forces on each other, you know. So this one is due to 1 on 2, and this is same force due to M2 on M1, and collision T1 to T2. So it's a time-dependent large force, and it gives a momentum or impulse from T1 to T2. Okay. So usually these forces are contact collision forces, and these are in a short time, and they are big in magnitude. So you may have, for example, on the system M1, M2, I have just separated them. This is the F collision, this is the F collision. But for example, you may have an external force on them both, FA, external. And this force may be, for example, a gravitational force. It's just that this T1 and T2 is so small in collision time, and such forces will be so small so that collision, impulse due to the collision and impulse due to other reasonable forces like gravity, etc., this is like J collision. So these are negligible. What this means is that negligible. What this means is that before T1 and after T2, system will proceed under the influence of these external forces, for which the total momentum may not be conserved. But during the collision, it will be conserved. So collision is a special process that occurs hard and fast. This is what we will take. Now, so this was a side remark. Now we have two momenta here, P1 and P2. But collision is such that the total momentum, PCM, is conserved. If the total momentum is conserved, then a body which has a momentum has a kinetic energy P square over 2m. So because we have a center of mass momentum, there is a certain amount of energy locked in the center of mass motion. This is PCM square over 2m, where m is m1 plus m2. So you may observe this process on the ground, let's call it the lab frame, m1 and m2 moving, colliding, and then they have their final velocities, etc. But what you see is an entangled version of this motion, okay? Because it's entangled with the, what's happening is entangled from the lab frame view with the center of mass motion. So since center of mass momentum is conserved, since part of the energy is always locked in, then this is not playing any role basically. What the dynamics lies elsewhere. What is changing lies elsewhere. So to understand what is the other momentum, because from P1 to P2 we pass to P center of mass and some P, which we don't know yet. Okay. So what can we, how can we find this P? One way is this. Look, let's look at the energy. P1 square over 2m1 plus P2 square over 2m2. And this is the total kinetic energy of the particles. And let's subtract from this the kinetic energy of the center of mass motion. And the remaining energy is the available energy for the dynamics. So let me just subtract PCM square over 2m. The idea is to be able to write this as 1 over 2, some p square and some m. Okay? But what is p and what is m here? Okay? So let's do a little bit of the algebra. This is P1's, PCM is P1 plus P2. If I square it, P1 square plus P2 square plus 2P1 P2 over 2M1 plus M2. Let's look at this subtraction. Because I don't have much space here, let me just erase this part. So let me just look at the P1 square term. I have 1/2 P1 square, then I have 1 over M1 and 1 over M1 plus M2 minus 1 over M1 plus M2 plus the rest. Let's work with this one. M1 plus M2 minus M1 divided by that. So this gives me M2 divided by M1 times M. Let me multiply by M2 over M and divide by M2 over M. Namely, I multiplied by 1. And let me write this thing equals to this thing times that. 1/2 M2 over M P1 square divided by, so I took M2 over M and I took M2 over M. What is left is M1 M2 over M. M1 M2 over M. This is that term and that term. Now, this expression is symmetric between the indices 1 and 2. If we change the indices 1, 2, 1, 2, nothing changes here, and nothing changes here and there. So I know what is the other one. The other term is, so I have P1 square over 2, M1, M2 over M. The other one I can immediately write, P2 square over 2, M1, M2 over M. Now the third term, minus 1 over 2, P1, P2 over M. And I multiply by M1 over M, M2 over M, and divide by M1 over M, M2 over M. And this thing cancels. So, all right. And here's the 2 that I forgot. I inserted here. 2, okay. So let me write it to the top. So in the bottom of these terms, I have 2m1 over m2 over m, same denominator. So it is 1 over 2, m1, m2 over m. And upstairs, it's a square. I should put here m2 over m square, 1 over m square. So it is m2 over m p1 minus m1 over m2 p2 square. So you see, this is indeed coming out in this form. So let me erase what is filling up the blackboard. Kinetic energy of the 1 plus kinetic energy of the 2 minus the kinetic energy of the central mass is 1/2 p square over 2 m reduced, where now p is defined as m2 over m p1 minus m1 over m p2, and this m is called m reduced, is m1 m2 over m1 plus m2. So let us call this kinetic energy of the relative motion. So collision is basically what is happening to the kinetic energy of the relative motion, depending on the type of the collision. Okay? So forget about the center of mass motion. It is moving constantly. It has trapped constant energy because it has momentum. But that's not the dynamics. Dynamics is what is happening in the relative motion. So from P1 and P2 and M1 and M2, we transform to two imaginary masses, the central mass, M1 plus M2, and the reduced mass, and the center of mass momentum, and the momentum of the relative motion. So P, if I write P1 and P2 as M1, V1, etc., this is M2, M1 over M, V1 minus M1, m2 over m v2, that is m reduced, this thing, v1 minus v2, and this is the v relative. Okay, the relative velocity of v1 and v2. If v1 is larger than v2, it will come and hit on the mass 2. Let us compute P1 and P2 in terms of, so let's make this transformation, P1 and P2, PCM and P. So let's find each momenta like this. So let's write P1 plus P2 is equal to P central mass and M2 P1 minus M1 P2. It is M times P. Let us solve for P1 and P2. To solve for P1, I multiply this thing by M1 and add these things, subtract out, and P1 is equal to M1 P central mass plus MP, or P1 is equal to M1 over M P central mass plus P. And P2, to find P2, I eliminate this thing, I multiply by M2 and I subtract. So this picks up a minus sign. So this is M2 over M P central mass minus P. So this is the transformation from the P1, P2 problem to PCM and P problem. And since this is constant, you see none of these was constant, but this will remain to be constant. So what is changing in the problem is really just P. So a two-body problem is effectively reduced to a one-body problem. Okay, by an abstract transformation. There is no total mass at the center of mass. It's just a mathematical concept. And we have only real masses M1 and M2. There is no real M reduced. And yet the physical picture is most clear in terms of these variables, because it's now a one-body problem. I'm erasing this. So these are so far our results. Let us denote the variables in the center of mass frame by prime. So P1 prime, that's P1 in center of mass frame. But in the central mass frame, central mass is at rest, and the central mass momentum is 0. So P1 prime is equal to P, P2 prime is equal to minus P. So if you are at the central mass, M1 is coming to you with V1 prime, and M2 is coming to you with V2 prime, or momentum P1 prime, P2 prime. This is P, and this is minus P. So looked at it this way, we again have two particles whose velocities or momenta computed in the central mass frame. But let's look at the energy. So 1/2 M1 V1 prime square plus 1/2 M2 V2 prime square. So if you just add the kinetic energies of these particles in the central mass frame, but we just did that, we know that this is simply P square over 2M reduced. I don't need to calculate because we already calculated it. Okay? So basically we don't have two particles. Just look at it this way. This is the center of mass frame, and here is the P of and M reduced. Okay, so that's the initial thing in the center of mass frame. A fictitious particle with mass M reduced is coming to you with the relative momentum P. The question is, what happens afterward? And this is what we are going to discuss. I want to point out one more point about P. P, for example, is M1, M2. I'm just copying down from here. M1, M2 over M, V1 minus V2. If you subtract from both V1 and V2 the central mass velocity, this is the same thing as M1, M2 over M, V1 prime minus V2 prime. So this was in these velocities are written in the central mass. These velocities are written in the lab frame. That means the relative momentum does not care whether you are in the center of. It does not care about the value of the central mass momentum. It's an independent variable. Okay, something is happening in the train. It doesn't matter whether the train is going fast or slow. All right. Now we can discuss the type of the why are we doing this? We are reducing a two-body problem to a one-body problem with hope that solutions of the one-body problems are much more easy, fast, and we can understand what's going on. Now, so initially, we are in the central mass frame. There is M reduced is coming with initial relative momentum. So Pi is M reduced V1 minus V2. It doesn't matter in which coordinate frame I write it. V1 minus V2. And I will, this is the initial. This is V relative initial. Okay. Obviously, you want V1 to be larger than V2 if they are both moving in this way to hit. Otherwise, there would be no collision. All right. That's the beginning. Now, what happens at the end? At the end, we have a PF, so this is initial. Final. Now we can write final PF immediately. PF is equal to M reduced from here, V relative final, which is V1F minus V2F. But one would think V1F should not be greater than V2F because otherwise it will hit again, and that PF should better look to the left in this picture. So let's write it in the with the vectors. It will simplify one dimension. So let me call this vector I or X. PF is M reduced V relative F times I. I want this vector to look the other way. Okay. So if I write it as minus M reduced minus V relative F I, then it is M reduced minus V relative F times minus I. This is the unit vector. And let me define UF tilde. UF tilde definition is minus V relative F, which is, this was V1I minus V2I. So this is V2F minus V1F. Okay. So this is equal to m reduced because it is minus I will take write it like this now. M reduced UF tilde minus I. What happened? I brought it to this form. Let me write here. Minus I looks to the left, so it is this way. PF is equal to M reduced UF tilde. That means if UF tilde is positive, PF looks to the left. If UF is negative, then PF looks to the right. Why did we do it? Because it is a better physical picture. PI is coming in and PF going back. So now let's look at different types of collisions. Now it's easy to discuss. One is the elastic scattering. So, P initial, this is the relative momentum, okay? So it is M reduced V relative I. It is coming in, and here PF equals PF in this direction, M reduced UF tilde, and if UF tilde is equal to V relative I, then K relative initial is equal to K relative final. Okay? The initial and final translational kinetic energies are the same. So this is the elastic scattering. Or if UF is less than V relative I, then that means we have lost some energy. Okay? So the energy balance we can write like this. KE relative initial is equal to KE relative final plus Q. So if Q is 0, we have elastic scattering. If Q is positive, that is some energy is pumped and wasted to outside environment, then you have lost this kinetic energy. How can we lose energy to the environment? That is to degrees other than the translational motion. Namely, two objects are bumping to each other, they may deform, there may be heat. Okay, that all those deformation energy and heating energy goes into Q. So that's inelastic. And the last thing is if one hits 2 and 1 and 2 move together. They stick. Okay? This we shall call completely inelastic. Completely inelastic. That means all of the Q is equal to initial relative energy and relative kinetic energy of in the final case is 0. That means if you look at the picture, this is the P initial, and finally, well, we are here and it's not moving anywhere. Okay, the whole kinetic energy is lost. Now there is one more point which sort of generalizes this elastic scattering, is that you can pump in energy, take energy from the translational motion, put some of it in the relative translational motion, but put the rest of the energy into harmonic potential or some rotational kinetic energy. So we can say Ke relative E is equal to K relative F plus U potential. Perhaps there is some kinetic energy rotation. We shall still refer to it as elastic, namely because we can account for this energy. But if it's irreversibly lost to deformation and heat, that will be Q. All right. Now, there is one interesting thing. I will erase this part. So, as you see, two objects colliding and then having different velocities, you can do it all of these without transforming to central mass frame and the relative coordinates by brute force. But even if you do the algebra right, the outcome is not so physically appealing, whereas here we have a very simple picture. Okay. One thing we may add here is if M2 is very large, so that M1 over M2 is going to 0. That's the wall problem. Wall. So here we have a wall whose mass is almost infinite. Here M is coming. So let's look at here in this problem. M1 V1 initial plus M2 V2 initial. This was at rest, so this is exactly 0. So M2 is very large with respect to 1, but this is 0. This is equal to M1 plus M2 V central mass. So V central mass is M1 over M1 plus M2 V1I. But M2 is very large, so this is basically like 0. So this is like 0. So central mass velocity is 0, which means the lab frame is the central mass frame. Okay. So what happens to the reduced mass? M reduced is equal to M1 M2 over M1 plus M2. Well, M2 is big, neglected, M2 is cancelled. So this is like M1. So M reduced, let's say, comes with the relative velocity V, 1I. Here it is. And then this is the initial. And in the final, it goes back. And this is again V1I. And M reduced is like M1. So M1 comes with a certain velocity, bounces back with the same velocity. Okay. A variation which can be solved trivially is this. Let me erase this part. What if the wall moves? Now, if the wall moves, remember the central mass is with the wall. So if the wall moves, central mass is moving to the left. So in the central mass frame, wall is at rest, but the particle, M reduced, which is the same thing as M1 we just showed, it is coming to you with V plus U. This is at rest. This is coming to with V plus U. Because it is elastic scattering from the wall, this is the initial, and in the final stage, it is going back with V plus U. This is in the central mass frame. And now what is it in the lab frame? So this is the wall with respect to ground. I'm looking at the final case. And this is the mass M1 with respect to wall. and m1 with respect to ground. So this is u, this is u plus v. So m1 with respect to ground is moving with velocity v plus 2u. So it gains this 2u. Obviously, the kinetic energy in the lab frame, the kinetic energy of the particle is not conserved, but that's okay because of the limiting case that m2 is so very much larger. Now we discussed so far two particles approaching each other on the very same line. Now we can still be in one dimension, but the lines need not be the same, but they may be parallel. I'm erasing this. So, for example, we may have two objects. Okay. This may be going this way. This may or may not go. Okay, this may be going that way. If this one catches up, now they are in their centers of mass are moving in parallel lines. They are not on the same line. Now, of course, there is this angular momentum in the game. If there is no external torque on the system, okay, angular momentum will be conserved. But let's look at the angular momentum of the motion. Here, somewhere in this line, we have the central mass of this object and of this object. Okay. So let's this be object 1, this is object 2. And if we look at the central mass frame, this is the position R1 prime, and this is the R2 prime. I'm drawing an arrow, position arrow from the central mass to the central mass of the object. Okay, and this one has P1 prime, this one has P2 prime. So the L central mass of this thing is R1 prime cross P1 prime plus R2 prime cross P2 prime. But we showed that P2 prime was this, P2 prime was minus P1 prime in the central mass. So this is equal to R1 prime minus R2 prime cross P1 prime. P1 prime is simply P, which we showed it at the beginning. And R1 prime minus R2 prime is R1 minus R central mass minus R2 minus R central mass. So these things cancel again. R1 minus R2, which we shall denote as R. So this is R. So we have a very simple formula then. L central mass about the system's central mass is equal to R cross P. This is due to the orbital motion of the reduced mass plus, I did not write it there, but plus L spin 1 plus L spin 2. Namely, there may be angular momentum, additional angular momentum, because they are rotating about their axis passing through their centers of mass. So this is a very nice and simple formula. It shows that we can compute the angular momentum due to their translational motion very easily. Okay, next, this finishes the first part, A, and we'll take a break for a minute, and then I will solve two simple problems showing the use and effectiveness and the speed with which we can solve these problems.